Yep.
Okay, so the paper I'm going to present is by Richard Gilbert and Charles Shapiro, and it's about patents and how to design them optimally in their structure. So what are patents? They are a way to reward innovators for their effort to foster innovation by rewarding their and incentivizing their invest in the innovation of the patented good. This reward takes place in allowing them to exclude other competitors from profits over the patented good, and also means that other firms that want to innovate on the same product, on the same path, cannot. I mean, it's also the number of. It means that the other producer has to wait for a number of improvements before obtaining a non-infringing the existing patent, another patent different from the existing one. So the structure of a patent is consists basically of patent breadth and patent length, where patent length is quite straightforward, is the lifetime, the duration of the patent, and the breadth as a less immediate definition, because it's the extent of the coverage of the paper, of the patent, meaning the extent to which the patentee, who is the holder of the patent, can exploit his exclusive right. In this paper, the profit flow that the patentee makes from the beginning of the patent to its expiration will be considered as a measure of breadth. So the question addressed by the authors in this paper is how to, which is the optimal mix between those two things to design a patent in an optimal way. Their main finding is that, from a welfare point of view, a patent is optimally designed if it's long in duration and narrow in scope, where the scope is the scope of protection of the patent, meaning the extent to which the patentee profits are protected by other competitors. So this general result, this main result, is achieved by this model, where T is the length, so the lifetime of the patent, P is the breadth, the profit flow, as I said, and the social welfare is a negative function of the profit flow of the patentee, which is going to be critical assumption, because we are going to assume that there is a dead weight loss linked to increasing patent profits over welfare. P bar is the expired patent profit level. So when the patent expires, profit flow of the patentee decrease up to this level, and consequently also the welfare reaches this level, which is higher than before. And then we can also express the breadth, the profit flow as a function of the lifetime of the patent. So this is an expression for the social welfare as a continuum over time. So this is the time where the patent is during its lifetime. This is afterwards, and the same have is here, and this is the present value of the profit flow of the patentee. So our aim is to maximize social welfare subject to this incentive compatibility, participation constraint for the patentee. And as I said, our crucial assumption is that welfare is concave in the patentee profits. If we express the patentee profit as a function of the patent length, the minimum reward that the patentee wants to has to keep to participate and to foster innovation is this one, and we can also express social welfare as a function of T, actually, as the patent length. This is the first order condition expressed in this way. So this derivative, if you consider, well, with all the computation we arrive to this derivative, and given this crucial assumption, we eventually say that social welfare is increasing in the lifetime of the patent, which means that eventually, hypothetically, infinitely lived patents are optimal. In this paper, they consider patent breadth as the ability of the patentee to charge prices of the patented goods more than their competitive level, because the patentee can benefit of a monopoly during the lifetime of the patent. In this sense, they also focus on patent policy has the ability to define the goods which are substitutes in consumption to the patentee good. And here they make a distinction between their work and a work made in the same year by another analyst, Kemperer, where Kemperer actually finds a result which is completely opposite to theirs, because he finds that optimal patents are short in duration and wide in scope. And this happens because Kemperer claims that when patented goods offer a variety of characteristics to consumers, they are not that willing to change and substitute for other goods, even if the price of the patented good is high, because they don't suffer great disutility by paying a higher price for a good which has the characteristics that they prefer more than a good that has a lower price and it's more convenient, but has less characteristics compared to their preferences. So that's why he argues that the wider is the coverage of the patent, the higher is, the power of the patent. So they should be short their lifetime should be short, but they should be wide, so there's no rate that loss in welfare. So the crucial thing to prove in the going back to the Gilbert-Shapiro model is to prove that welfare is concave. To prove this, they rewritten social welfare as the difference between total benefit and total cost, and in this way the profits of the patentee, where Px is the demand for the good X, and they define G as an inverse function of the profits. The crucial assumption here is the negative first derivative of the profits. So if this holds, if actually profits and and welfare are concave in output, it can be proved that welfare is concave. Because if we take the second derivative of this thing, of welfare as defined in this way, we found that this is the second derivative, and given those assumptions, we eventually find that the only way in which since G is the inverse function of this first derivative is this one, and the second derivative computed is this one, and it's negative. So the overall second derivative here is negative as well. Even if this assumption doesn't hold, because this is a weak assumption, so it can be relaxed. It can be also shown that starting from, let's say, this point and taking this point as a optimal policy, moving from this point leads to something that is not optimal because it reduces welfare actually. But at some point we have this concavity that we want again, and this happens when marginal benefit for the patentee is closer to marginal cost, so it's closer to a competitive framework, and for small, when the reward for the patentee is small. So we can still, even if this assumption is relaxed, there's an interval of patent breadth which happens for a smaller reward, so for a narrow scope, where this holds, and infinite living patentee are optimal with narrow scope. So in conclusion, this paper argues that optimal patents are designed with long living patents with a narrow breadth, but there are some critical points about this. The first is the comparison with the Klemperer results, because Klemperer reaches a completely different result. But the most important limits are on the assumptions, because I didn't mention this, but this model holds for a stationary and predictable environment. Stationary meaning that we consider only one innovation, and we don't consider that innovation built on each other, and that when an innovation is done, there's also innovation fostered in related fields, and in this case, innovation in related fields can be stuck because of the fear of other innovators to bump into the field of the covert patent.
Okay. No other questions? Okay. Just